Hello everyone. Uh, Today we will start the assignment number 3, which is based on the Mendel SSH crystal structures, and we will discuss about the how to index a plane, how to find out the Miller indices of a plane, and the direction, which are the plane for the what is the atomic packing fraction for the HCP, FCC, BCC coordination number. This assignment is all about this one. If somebody has any query, please let me know. Otherwise, you can message in the chat box also. I will check this and kind of, uh, I mean, will give a solution for the problem one. Okay. So today, let's start with the let's start. Okay. Let's start with the question number one. That is, one is basically the here you have to find out the Miller indices of a plane that make an intercept of 1 on a-axis, 2 on the b-axis, and it is parallel to the c-axis. So we have the cube. Let's say if we have a cube like this, it's a simple cubic where the atoms are present at the corner of the cube, and here it is mentioned that if this is my a-axis, this is my b-axis, and this is my c-axis. It is defined here. It has intercept 1 on the a-axis, 2 on the b-axis. I am writing here the intercept 1, 2 on the b-axis and parallel to the infinity. So if some so here it is 1 and 2. If it will be double something, I'm assuming it here. So this is plane it like this plane, and this will be the infinite one. It will go like this one. It does not intersect at the c-axis, so the intercept on the c-axis will be the infinite. So how we calculate the Miller indices? First we take the reciprocal of the intercept, so this will become 1 by 1, this become 1 by 2, and this is 1 by infinity, so it's become 1, 1 by 2, and this is 0. Now the Miller indices are the simple integer numbers, not the fraction numbers. So we will multiply with the 2, and we take the set of integer in the smaller number, the smallest set, whatever the possible here. So we will multiply it by 2. So this will become 2, 1, 0. So the Miller indices of the plane that has an intercept 1 on the a-axis, 2 on the b-axis, and it is parallel to c-axis will be the 2, 1, 0. So B will be the right answer for this one. Okay. Okay. Let's move to the next question here. In this question, this is the Miller indices of a plane that makes an intercept of 3a, 2b, and the c along the three crystallographic axes, that is where a and b, c are the primitive vectors of the lattice. So similarly that we have done in the question number 4, similarly we will proceed with that one. So first we write the intercept one, then we take the reciprocal one, and then we will multiply the number so that we get the set of the smallest set of the integer one. So here the intercept is, this is 3a, 2b, and b. See here the a, b, and c are the primitive vectors of the lattice. So first we have to find out the intercept on the respective axis, that is a, b, and c. So we have to divide it with the a, this is b, and this is c. So it become 3, 2, and 1. Okay. So now take the reciprocal of the intercept. This will become 1 by 3, 1 by 2, and this is 1. Now the common integer will of this one will be the 6, so we will multiply with the 6. So this will become, so it will become 2, 3 and 6. So the Miller indices of the plane that is having the intercept of 3a, 2b and the c along these three crystallographic axes will be the 2, 3 and 6. So my C will be the right answer. If somebody has any doubts, so please let me know. We will discuss that one, or otherwise you can message in the chat box. We will come to that point also. Okay, so basic idea for the to find out the Miller indices is first we have to take the intercept one, whatever the intercept on the primitive letter vector of the lattice, and then we have to find out if either it is given in the number or it is given in the term of the primitive vectors. So there you have to take the consider only the intercept one, not in the term of the lattice vector. Then you have to take the reciprocal one, and then you have to convert into the smaller set of the integer one. So this is the simple procedure for the Miller indices that you can find out. So question number 1 and 2 all about the Miller indices. There you have to find the Miller indices. In the next question, there you have to in now see in hexagonal system the Miller index is 2, 1, 0 and minus 1, 1, 3 could be converted in the following Miller-Brevis indices. See, in FCC, cubic and orthogonal, in tetragonal, in all these system, if I'm talking about the cubic one, all there, we define the Miller indices by the three set of numbers. That is, let's say H, K, A, L. But in hexagonal, we define the Miller indices by the set of four number. Set of four number. That is my H. Just a second. Okay, so for the hexagonal, we define the Miller indices by the four numbers, that is my H, K, I, and L. And also here the direction is also defined by the four integer. Generally, we define the direction as U, V, and W, but in hexagonal, we define with the U, V, T, and W1. Okay, so what is the relation between my the normal Miller indices and the Miller-Brevis indices? So there is the one. So HKL is in HKL we have my this I, H and K. I is such that my H plus K plus I equals to 0. Or we can say that my I will be the minus of H plus K1. Okay, in here we have set of the relation between for the direction one as well. So remember this one, this will be needed uh, for this one, for this question. So of now we have the plane, we have 2, 1, 0 and another is the minus 1, 1 and the 3, 1. Okay, now you have to convert to the Miller-Brevis indices. So what will it becomes? Basically, I have to write in the form of H, K, I and L. Okay, so this will become 2, 1 and I will be the minus of sum of H plus K1. Here, see from here. So it will become 2 plus 1 will be the 3 and then minus of 1 will be the minus 3 and L will be the same. This is the 0. So it become, this plane become 2, 1, minus 3 and 0. Okay, now corresponding to this plane, minus 1, 1 and 3. I can write this as minus 1, 1 and 3. So what will be the Miller-Brevis lattice for the hexagonal one? Here it will become the minus 1, 1 and sum of the this one will be the minus 1 plus 1 will gives to 0 and negative of 0 is 0 basically. So this is 0 and the 3. So I can write it here like that. This is equivalent to minus 1, 1, 0 and 3. So for this plane 2, 1, 0, the Miller-Brevesel indices will be the 2, 1 minus 3, 0, and the for minus 1, 1, 3, it will be the minus 1, 1, 0, and the 3. So if I see the options, so I get the C will be the right answer. Okay. Pani, you joined the late. Do you, if you have any problem in this question or in the question, in other question, please either type in the chat box or unmute, otherwise unmute yourself and let me know. Okay. So this is all about the question number 3. If we have to, if you have given the Miller indices, why we are shifting to the four dimension the Miller indices in the hexagonal, because it is convenient. We have the, because in the hexagonal we have the hexagonal at the bottom or the center, so there we define A, B, C here only, but there is height, and this ratio, this height, or we call the C, it is not equivalent to A. So that's why we define the 4, so that it will be the easier to do the calculation or also visualize the hexagonal lattice one. Okay, so that's why we move to the Miller-Breves's lattice. Okay, so this is all about the Miller-Breves's indices. If you have to now, there is also one about the I mean the direction as well. So direction in the three I mean normal Miller indices we write with the U, V, W, and here we write as the U, V, T, and W. So what will be the relation between this one and this one? So this my capital U is equals to 2U plus V, and capital V is equals to 2V plus U, and W is my same W, and T is equals to minus of U plus V, small u plus 1. T will be the same U plus V. So this is the relation between this is for the direction one, as we denote my direction with this bracket one, and this is the relation for my this one is for my plane. So HKL will be equivalent to the HKIL, and I is equals to minus of H plus K. So this one. Okay. So in this way, we can convert our Miller indices to the Miller-Brevesel indices one. Okay. So now let's move to the next question. So here it is the, now here you have to find out the atomic packing fraction of the HCP lattice in percentage. You have to find out. So what you all know about, as the professor already taught you about the all the lattices one. So HPC, in HPC we have the hexagon at the bottom, and as well as the one hexagon at the, or we can say this HCP is made up of the 3 units that we, if I say this will be go this way, this will be this way, this, there will be the 3 atoms at the center at a distance of 1 by 2. Okay, and the one atom it is present here. It is not properly diagram, but you can visualize. Here are my atoms. Is it visible to you? So this is one of one lattice. If I say it is made up of the 3 lattice, as I told you, this will become 1, this is the one of them. Another will be the this one. Let me do it with the different color. So this will be the another one, and third will be the with this one, this plane and the this plane. So now we have to calculate for the atomic packing fraction. As you know all about, the atomic packing fraction is how closely my lattice is packed, how much space is covered by the atoms and how much space is there for. So this atomic packing fraction will be the n effective number of effective number of atoms in a unit cell into the volume of the atom and divided by the volume of the lattice cell. Okay, so this is case for the 3D one. If somebody asks about the 2D one, so this atomic fraction, I'm writing it as a APF. So this will be the again an effective and the this is the area of the atom, one atom, and because and we are just multiplying. This is the unitless quantity because this is also if I see from here, this is only the volume divided by the volume. Okay, so it will be give you a fraction number between 0 to 1, and if I'm want to in the percentage one, yeah, you have to multiply with the 100 one. For the 2D, it will be the N effective. N effective is generally a number, how many atoms are there in a one unit cell. So N effective will be the N effective into the atomic packing fraction will be the N effective into the area of the atom will and divided by the total area of the unit cell. Okay, so this is the way we calculate the atomic packing fraction. Here it is about the hexagonal closely packed lattice. HCP is your basically hexagonal closely packed lattice. Hexagonal closely packed means your three atoms will be inside at the hexagonal. It will be the one layer of atom. So this will be, if I visualize this one, will be the this one. These have the same atoms. Again, this is one layer. If I'm saying this will be the one atom, and another atom will be sitting at this position. So this one, like this way, this way, and again the it will be the same as the again the atom will be lie here. Or let me draw it with a different color. So there is a closely packed. They are the closely packed here. So this is the kind of the hexagonal. If I view from the top view, okay. Now we have to calculate the atomic packing fraction. So you all know the N effective. First we have to calculate the N effective one for the HCP. So N effective 3 atom are inside. So there will be the 3 atom. This one for this atom, this one and this one. These are shared by the 2 unit cell. So the contribution for this atom will be the 1 by 2. And now the number of how many number of atoms that are shared by the two lattice cell will be the 2. So this is 2 and plus now I'm considering the corner atom. These corner atom are shared with this 6 unit cell, and the or we can say this atom has a contribution to the 1 by 6 to the this hexagonal one. And so this will be the and how many numbers are in they are I mean these are the 6 at the corner of the hexagonal. So 6 will be the 1 by 6. Same with the case with the down. This is for the top one and this is for the down one. So this will become for 1 by 6. So this will become, this give me 1, this is also 1 and this is also 1. So this is so N effective for the HCP will be the 3 4, 5 and 6. Total will be the ineffective will be the 6. Now we have the hexagonal at C. Here my, if I'm C, you all know the for the hexagonal my C by A ratio, that the height versus with the A, the side of the hexagonal is by root 8 by 3, that we have done in the classroom. So if I'm see the plane of this hexagonal plane of the HCP, so this is the y and this is my A distance, and my atom are sitting like it here, like this way. I mean this A distance it covered by the two atoms. So this is if R is the radius of the atom, so this A will be my 2R. Okay, now put all this value in the formula and we will get, okay, let me do it here at the end. So A will be number of N effective is 6. APF will be the N effective into my volume of the atom, one atom in the set, and the total volume of the unit cell. Okay, so N effective is 6 and volume will be the, we only the, we consider the all the atom are the sphere, so volume of the sphere is equal to 4 by 3 pi r cube. And volume of the hexagonal structure, if I'm considering the volume of the hexagonal structure is, volume of the hexagonal is 3 root 3 by 2 a square c. So this will become 3 root 3 a square c by 2, and we already know a is equals to 2r. Okay, so my r will be the a by 2. If I substitute here, this will become 8 pi this is a cube divided by 8. 2 will be the divided by 8 multiplied by 3 root 3 by 2 a square c. Okay, so 8 will cancel out. It will become, this will go 2 pi, this also a by 3 root 3 c, and we also know that c by a is equals to root a by 3. If I put the value, then a by c will be the root 3 by 8. So this becomes 2 pi by 3 root 3 multiplied by root 3 by 8. So root 3 will be the cancel out, only we will remain with the root 8. So root 8 I can write it 4 into me 2. So this will become 2 pi 3 into 2 into my root 2. Okay, so 2 into 2, it will cancel out and it will become pi by 3 root 2. And if you calculate it, it will come out for that CPA will be the 74%. Okay, calculate this value. It will come if this will give 0.7. If you calculate in the percentage, it will give the 70%. Same thing we can do with the for the simple cubic one and the for the BCC and the FCC. In simple cubic, you know the this is n effective will be the 1, and in BCC you have the n effective is your 2, and in FCC the n effective will be the 4 1 for there. But you have to consider what is the relation between the A and R for the FCC, for the BCC, and the so for simple cube. Because we have used this, na? Because volume will be the volume of the atom will be the same. That will be the 4 pi R cube. But A, the relation between the A and the R will be the different for the different crystallity. For the simple cubic, A will be the 2R. For the BCC one, it will be the root 3A will be equals to the 4R, and the FCC it will be the root 2 equal to the 4R. These things the relation between all these we have discussed in the last class, and once you find out the n effective, then you have to put in the value, and that will give you the uh, atomic packing fraction. And the atomic packing fraction, if you put these values, so the atomic packing fraction for simple cubic will come out around 0.52, and for BCC will be around the 0.68, and for FCC will be around the 0.74, and the HCP has the same also, that is the 0.74. So my FCC and HCP are the my closely packed compared to the other. Okay, so this one, so we were here. So the atomic packing fraction of HCP lattice will be the 74% one. Okay. Does anyone have any doubt in this or in any atomic packing fraction one? Does anyone have? No one is responding, so I'm assuming that everything is all right. So let's move to the next question. Okay. So this question, in in this question also we have to find out the Miller indices. Okay. Thank you, Pani, for the responding. So in the next question, so it is all about the here we have also find out the Miller indices of the shaded plane drawn in the hexagonal unit cells shown in the figure. So this is the figure they have given, and we have to find the Miller indices of the shaded plane. In the question number 1 and 2, we also find out the Miller indices, but there we have you consider the units, the simple cubic one, or the yeah, or the other. We haven't considered the hexagonal one. So we point out how to find out the Miller indices. First, I'm just repeating again because some of you are join late. So Miller indices will be the first you have to calculate the intercept one, then you have to take the intercept reciprocal of the intercept one, and then you have to consider it multiply set integers so that you can get the smallest set of the integer. The smallest set of the integer will be your Miller indices. So for this one, you all know in the hexagon, there you have to in Miller-Brevis indices, you have to find out in the Miller-Brevis index in the four thing, because in the hexagon we have the C also. This one lattice is also C. So first we have to find out the for the this shaded plane, what are the intercept one. So if I'm considering this one, now this is one direction is my A1, another is A2, and this is my A3, and C will be the my this the perpendicular direction here, this one. So for this shaded one, so this shaded plane intercept at A1 at a distance of if I say this as at the 1, or yeah, we can say the at the A1. A1 is written for the axis 1, so I'm just considering it is the because at 1 unit, this plane is intercepting at the 1 unit of the A1, so this is 1. And if for the A2, so it is not intercepting at the A2 because it is parallel to this. If this is also parallel to this is also so this is not intercepting at the A2. So this is will be the parallel for the parallel one. It is not intercepted. So intercept will be the infinite one. If I'm considering for the A3, for this side, A3 is in the this direction because my A2 will be in the if I'm seeing there, it will also not, it is parallel to this one, it will not intercept anywhere. So A3 in the negative of A3, it is intercepting it here. So this will be there of minus 1 because it is at the 1 unit in the negative direction. For the C, if I'm saying this is the direction C, so it is also intercepting it at a 1 unit distance at the in the C direction. So this will be the in the C direction. Here we write the intercept at A1 at direction in the direction of A2, A1, A2 and A3 and in the C direction. Now these are the intercept one. Now again you have to take the reciprocal of this one. This will become 1. So 1 by infinite it will give you 0 again. So 1 by minus 1 it will give you the minus 1 and this is 1 also. So minus 1 and 0. So I can write this as a 1, 0, minus 1 and 1. So this will be the my Miller indices for this shaded plane one. So my B will be the right answer. Okay, is it clear for everyone? Okay, okay, let's move to the next question. That is the question number 6. In the question number 6, what they have asked, the indices of the direction that result from the intersection of 1 1 0 plane and the 1 minus 1 0 plane within the cubic lattice. Okay, so we have the two plane and we have to find out the intersection, the indices of the plane that in the, because these two plane, if I'm say this is the negative one, these two plane, these two plane, they are intersecting, and whatever they are intersecting, and we have to find the indices of the direction of that plane. Okay, now we have to find out the direction, in which direction with they are intersecting. So in the cubic crystal we know that the if HKL is my the plane, so direction will be the of HKL plane will be the HKL. Same for this one, for the 110 plane the direction will be the 110, and the for same with the 1 minus 10, so direction will be the 1 minus 1 0. Okay, yes. Okay, so now we have to find out the intersection of the, and we intersection will be they are I mean in the intersection there will be the direction that will be the perpendicular to the both one, because if we have to go, so we will take the, if we have to consider in the same direction on the in the parallel case, there we took the dot product for the perpendicular or the direction intersection one, there we calculate the, because see this plane, if this is my plane, so this is my direction. Okay, and this is the another plane, so this is my direction. So I have to find out the that plane that is having the direction, that is another plane, this is the plane, so this will also the perpendicular, so this direction will be the perpendicular to this one and this perpendicular to the also one. So for this one we have to take the cross product, and the cross product for with this will be the 1 0 0, if I say this one, and the this 1 minus 1 0, this will give you, if I calculate the cross product of this one, so this will give the 0 for this one, and yes 0 here it will be this also, for if I'm considering the this way, this will also give you 0, for the plus 1 it will be the minus 1, and then again minus 1, this is in the minus 2 direction. The first two are the 0 0 minus 2. Okay, now we have to find out the Miller indices. Indices are the direction one. So this will be the this 0 0 minus 2, or this will be the equivalent to the, if I'm consider I'm in the smallest set of number, so this will give the, I can divide with this one with the 2, so this will become 0 0 minus 1. Okay, so the indices of the direction that is coming from the intersecting of these 2 points will be the 0 0 minus 1. So it will be the not A, no, it will be the C part. Okay, is it clear? First, you have to take the find out the because for the cubic one, every HKL having the direction is HKL, same one, and the for the because each plane is perpendicular to its direction one, so direction will be defined by the by drawing the perpendicular this thing. So if we have to find out the intersection, so we also take the cross product of that one because that is also coming from the both the plane one. So there we will get the 0 0 minus 2, and if I'm reducing to the smaller set of num, so this will become the 0 0 minus 1. Okay, okay, so let's move to the next question. Okay, so this is the this plane is perpendicular to the following plane. This 1 minus 1 1 will be perpendicular, this direction is perpendicular to which plane? I can write this equation as a 1 x cap plus, if I'm writing this direction, let's say this is my a, in the lattice vector this will become the a, this is the minus y cap plus z cap. So this direction will be the perpendicular to the following plane. Is it perpendicular to the this one? So this, if I'm considering for this plane, no, it will not be. So what will be the plane for the perpendicular this one? See, this will plane will be the corresponding plane will be the this 1 minus 1 and 1. Okay, and so for the for the corresponding one, for the this plane, the perpendicular one will be the opposite to this one. This is the minus 1 1 and 1. Okay, and now the direction will be the again, or here it is asked only about the plane one, so otherwise it will be the minus 1 1 and minus 1. So your B, yeah, this B will be the right one for the perpendicular plane one. Okay, or the for the perpendicular one you can, otherwise if you have the two planes, here it is also plane, we have calculated the plane here, and from this direction we can calculate the plane one, and we have also given the plane one. You just find out the with the cos theta, and theta should be the 90 for the perpendicular. Find out this will be the h1 h2 plus k1 k2 plus l1 l2 under root of h1 square plus h2 square and k1 square plus n1 square into h2 square plus k2 square plus l2 square. Either you can find out this way, or yeah, this will be the in the cos 90 perpendicular one, 0 for the parallel one, and if it is 90 the theta 0 will be the 0 for the parallel one, and theta 90 for the perpendicular one. Because this direction is, this plane is also similar to this one, and this can also write as the minus 1 1 and 1, and this is also same as the 1 1 and minus 1 also. This is the family of plane basically. Okay, is it clear? Just find out with this formula for this one and check it once. This is also for the simple cubic. This will define the angle between the two plane one. First find out the plane corresponding to this direction, and then take the uh, I mean the cos theta between the two product. Or you can also find that the A dot B also, the magnitude of A and magnitude of B, the plane of cos theta 1 also. There you can also find out there also. Okay, so uh, let's move to the next question. Another one is the pattern of the atomic arrangement in the FCC phase center close packing is given as the following stack sequence. So the FCC, what will be the sequence one? If we have to find out the FCC, So what will be the atomic arrangement? Because we already know about the HCP1. HCP will be the your, just I tell you, it will be the A, B, A, B, yeah, it will be the B part. Pani, this is right. Okay. A, B, A, B, A, B. For this is the HCP, but if I'm considering the FCC, for the FCC it will be the A, B, C and the A. No, for the you have to correct, not for the, no, B is not the right answer. The, here it is asked about the FCC one, not the HCP. For the HCP is the AB, because again after putting the atom at the void between them, here putting the atom, again the atom will be the like this way. Otherwise somewhere will be the so it will the, in FCC it will be the ABC, again ABC and then ABC. For the FCC it will be, so my C will be the answer, not the B one. Are you getting my point? This atom, the third layer, one this again the this if I'm putting here like this way, this if I'm putting it here and again I'm putting the atom that is this because of this one, this is my FCC. And if I'm not putting here, this is at the gap between the between two these one, so it will give you the FCC one. So the for the FCC it will be the ABC, that is and in the question it is asked about the FCC one. For the FCC HCP it will be the AB. So this one, so C will be the my right answer. And also in the D part they have the use the same sequence, because A and B is the only one because A represent the atom of A kind, B represent the atom of all the atom of the B kind. So here also, because we can represent this ABC similarly as the ACB. Now we have the atom of the C type and the another layer will be there of the B type. So this we can write as this, or we can write as A, B, C, something, whatever, but it should be in the repeating manner for the FCC or HCP anything. So C and the D will be the this will be the C and D will be the right answer for the FCC. If somebody asks you for the HCP, so this will give you the AB one. Okay. Okay, now let's move to the next question. So now in this question, what they have asked is the which of the following are the equivalent direction in the tetragonal system? Which are the equivalent? So in in the tetragonal we have in the tetragonal one, in the tetragonal we have A and the C, that is A is not equals to and basically A1 and A21. Okay, so now that what are the two equivalent direction in this one? So whatever this I can represent this 101 as a, this is equivalent to 010, but it's not equals to 001 because your parameter in the x and the z direction are the not the same one. So this will be the, so this will this is not equivalent to this, only these two are will be the equal one. So this A part, yes, A part is correct. So what about the B part? This is 110 or 101? No, this will no, because it can't be interchanged at the C and the A direction because they are not equal. So this will not be the answer. So again with the 112 and 211, no, this will again also not, because both are not equal same. And here in the C1 there is the 111 and -1, direction is same, but only we have the direction, same direction. Sometime if I'm taking this atom, see, direction is all about the AB. So if I'm, so it will be the AB. If I'm taking about this one, so this will be the B one, but they are the equivalent. These direction, if I'm writing this or this way, these are the equivalent direction for this one. So this one also the equivalent direction, A1, so -1 1. So D is also the right answer. Okay, So for the tetragon, if it is asked about the cubic one, so the cubic one, this will also will be the equal same, but for the tetragon, it will not be. Okay, so A and D will be the right answer for the tetragonal system one. Okay, let's move to the question number 10. Okay, so in this question, they have asked about the what kind of the following symmetry that is present in the lattice that is we have given. So lattice shown below we has which of the following symmetry element. So here the atom are present here. So first one is the four-fold rotation, second is the two-fold rotation, and third is the horizontal and the vertical mirror, and D is the diagonal mirror. So you all know that we already discussed is the n fold is equals to, that is the 360 by theta. Okay, for the four fold it will be the theta will be the over 90 degree. If I rotate basically the 90 degree, two-fold is basically your when theta is equals to 180 degree. If you rotate this lattice with the 90 degree, same thing. If I'm holding it and kind of rotating this, just visualize this thing. If you are just holding this lattice and rotating with the 90 degree, will the this same lattice you will get or not? I mean, if I'm rotate this the same thing, same lattice, if this is the my square, if I'm rotating this as the 90 degree, so this will become this here, this will become here, this one, and all the atom also move like this. So will it the same one the earlier one? Yeah, because the atom are equally arranged and spatially equally spaced, and also so that's why and this is so this lattice will be the fourfold. If I am rotate with the no, so lattice will be in the atom, the motif basically the your motif will the remain the same, so that's why my lattice will be remain same, so it is fourfold rotation. Okay, so now if I'm rotating it with the 180 degree, now 180 and opposite one, it's like basically it's the flipping one, flip one, or you can say the rotator, not the flip one. Maybe I'm just assuming the considering the 180 will be the similar title. So if you rotate this is also with the 180 degree, so you will get the same one, equally spaced, and the same atoms are there. So it is also the two-fold rotation one. And the what about the horizontal and the vertical? If I'm putting the horizontal mirror here, so is it the lattice same? So are they reflector mirror reflection symmetry is there? Yes, because these are same. And if I'm putting it the vertical mirror here, so these are at the same. So this will be the secant. So it will be the horizontal and the vertical. And diagonal one also, if I'm putting here, so these are at the diagonal one also. So these four kind of the all the four type of the lattice are present in this lattice one. This thing we have discussed in the last how the symmetry is in the also professor has also told about this thing in the classroom last week in class one. Okay, so now we have different, there we have the symmetry, all about the symmetry. Now here and we have to also find out the what are the following symmetry element that are present in this lattice one. This is not the equally spaced and the same one. Here if you see the clearly one, these are not the same one. The if you take the reflection one, is it the same one? No. Here see, if I'm taking this as a horizontal, so okay, let's come to the one by one. Again your fourfold theta will be the 90 degree. If you rotate with the 90 degree, twofold theta will be the angle of rotation. Theta is your basically the angle of rotation. Theta will be the 180 degree. Okay, now let's come to the one by one. So in this one, the if you rotate this as a 90 degree, will it remain the same? Just hold it and the kind of same thing. Just rotate, only rotate with the 90 degree. Will you get the same thing? Okay, for we have discussed in the earlier part. So just you have to tell me for this one, will it be the same for the fold rotation or the two-fold rotation, the horizontal and the vertical mirror, and the diagonal one? For which one it will be the follow the symmetry one? Fourfold, twofold, or horizontal and the vertical one, or the diagonal one? A and B. Okay. A and B. Okay. I'm agree with your A part, the fold for rotation, but not with the twofold. Just look at that. I mean, just check with the this one, twofold rotation, and tell me. Because these are not the same. I mean, see here, and if I'm say here, if I'm say this is the different one. If I'm rotating this one at the 90 degree, so this will become at this one. This okay, this is I mean 120. So it will be kind of flip one. So this become the original will not be the similar to this one. How I can show you this one? Okay, let's see. So if I'm brought to the this as a 90 degree, so this will become as rotation. This will come, this become this point will go to here. So this will become this will become this, and this will become this, and here this point will going to, so this will become this, and because here these the portion that is in the inside the square one are the not the same. These are one and second, and again let's see if I'm focusing on this one only, this one, this is the smaller one and this is the bigger one, smaller one, and if I'm taking the again 90-degree rotation, so here so this okay, so this one will be the, if I'm considering, so this will become the this one, and it will become 90 degree with this. I can't show you this way. It will not, this part will not be the similar. Okay, we will discuss this again later with the, if let me think with this, because the horizontal and the vertical mirror, it is clear, because if I'm taking the horizontal here, this will become like this way. It should be for this one also, this will like should be, it should be the this one, if I'm saying it should be become like this way. So horizontal and the diagonal also, because these are not at the same distance, the this square is not the a similar one, so it will not follow this one, and this is the fourfold, and twofold we will discuss also. Twofold is also, if I am considered the 180, the rotation will be the, because here if I'm saying here the my length is here this one and this one, if I'm taking, so 180, and this one is the here this one also direction one. So if I'm considering the again rotating with the 180, so first I mean you have to take consider this giving, this will come at the this direction, this atom will come at the this direction, this at the this, and this will, and if this atom will come to this direction, this will become the another type of atom, so not this one, and this will be the bigger one, and this will be the smaller one, this kind of the atom thing. So it will not be the same as the original one. Okay, are you getting my point? I mean, it's uh, uh, okay, you are getting the 180-degree symmetry. How this can be? I mean, uh, okay, okay. Yeah, this it will be the, if no, this atom will goes to here this way in 180 degree. This will goes to here. This atom will goes to here, and this atom will goes to here. If this atom goes to here, again repeat. So isn't it will become this way, smaller than again, and because the portion is inside is different one. This should become like this way. If this atom going to here, and this is not similar to the earlier, here it is the larger one and it is the smaller one. Okay, we can show you, I mean, 180 rotation. What about the this one? If I'm considering this has now this is the this one is okay. Now the take the 180-degree rotation of this part. We have considered only this one. Okay. Now you have to take the consider the 180 rotation. 180 in the 90-degree. What it will become in the 180? See this in 180-degree. This will come at this point here in the negative direction. Here it will become to here. This point that is lying at the in the first quadrant will go to the third quadrant, and that is near to, so this will become to here, so this will become to this way. Now this way. Okay. And this atom that is present here, this will go to here now, and this is there is nothing here, so this will go to here again, so this is like this way. Are you getting my point? How this is the second fold is not two-fold rotation is not there. So if I'm taking this angle, so I'm getting this type of symmetry for the 181. This will become this one, and the same this for this atom will come to here, so this will become this way and this way. It will become like this way. Okay, so originally we have this one, and now it's becoming like this one. And if I'm considering this, or if I'm assuming this one, so this is also not the same one. So that's why your second fold symmetry is not existing here. Is it clear now? I mean, Pani, is it clear? I mean, if you just only focus on the small part so that you can figure it out how this is second fold symmetry is not existing here. Is it clear or not? I mean, just respond me. Okay, okay. Just only took a small part and just see if the change in your lattice one. Okay. Now in the question number 12, what you have to find out the spacing between the 200 plane of a unit cell is the half of that between the 100 planes, and that is the twice or the twice of that between the 100 plane, or the 1 by 4th of that between the 100 plane, and the same as that of the one. So what will be the spacing for the 200 plane for any plane? If I'm considering the unit cell, it is not mentioned what kind of the unit cell, so we are considering only the cubic one. So d is basically dhkl is basically a under root of h square k square plus n1 for 200. What will be the d interspacing will be the under root of under 2 square plus 0 0, that will plus 0 plus 0, it will giving you a by 2. Okay, for 200 plane, the interspacing distance is the spacing interspacing distance between the plane is a by 2. And now in the question they have asked compare with the 100 plane. So if I'm considering the for the 101 plane, so d will be the 100 plane will be the a under root of 1 square, that is 1 plus 0 plus 0, that is giving you a. So now what is the relation between this interspacing and the this relation? If I'm talk, so this d2 will be the distance of half of the interspacing between of 100 planes. So this is the right answer. So according to this one, so your a will be the right answer for this one. Okay, you know about the formula, just you have to plug in the value into the formula, and then you will find out it will come out to be half of the plane between the 100 plane. Okay, now let's move to the next question, that is the acute angle between the 100 plane minus 100 direction in the tetragonal crystal with the C ratio 1 is here they have mentioned that the ratio between them is C by A is equals to 1.5. Now the direction they have given in the acute angle between the two direction one they have to find out. So simply we can find out that this is the angle. If we have to find out the angle between, then we use the cos product of, I'm writing this direction. Okay, I'm writing this a00 as a lattice vector. This will become a x cap, y cap, it will become 0, so this will become the z cap. I'm not the z, c cap. Let's say this considers a1 and the a1, a2 and the a3 for particular the crystal lattice vector for the in the three direction a1 and a2. So this will become 101 will become a1 cap plus a3 cap. And what about the minus 101? It will become the minus 1 a1 cap, 0 again, plus the a3 cap. Again, we know the cos product formula, that's the a dot b, because we have considered the vector. This is the second way we can calculate here the angle between the direction also. So this will become the a dot b will be the mod a vector plus mod b and the angle between them. So a dot b, if I'm considering taking the dot product of this one, this will become the minus 1 minus 1 plus 1. Is it the right one? Or is it something is missing here? Okay, minus 1 plus 1 here, or we can say this is a1 in the, because here the direction is a1, I'm considering the 1 unit, so a1 x cap, or say let's say this. No, the a1 is I haven't considered the a whatever the unit, because here the c by a ratio is not the 1, because they are having the a units. So I have to consider this as at a. In this direction the lattice constant of the, this is a and this is a and this is the c1, we have to consider along with this one v. So it will become the a1 cap plus c, that is my a3 cap. Okay, for this one it will become the minus a1 cap plus c a3 cap. Now just take the cross product one, a dot b will be the magnitude of a plus magnitude into magnitude of b and cos theta, the angle between them. So taking the dot product of one, this will become the minus a square and plus the a square. Okay, this dot product will give you a into minus 1, this is minus a square, c into c plus c square equals to, now the magnitude of a, this will of the this vector will be the magnitude of, what will be the magnitude of this one, this will be the a square plus c square. For this one, minus a square will be the a square plus c square. So this will become a square plus c square, again magnitude of b also, under root of a square plus c square and the cos theta, the angle between them. Okay, this will become the minus a square plus c square and this will give me a square plus c square, multiplying the square root will cancel it out and this will become a square plus c square cos theta. So cos theta will be the minus a square plus c square divided by a square plus c square. If I'm taking the minus a, because they have given the c by a ratio, that is the 1.5, so I'm taking out the a from a square from this one, so this will become minus 1 plus c square by a square upon 1 plus c square by a square, and just put the value here, this will become minus 1 plus 1.5 square divided by 1 plus 1.5 square. Just put the value here and find out the theta for this one. Take the cos inverse of the this value, whatever this value is coming, just take the theta of the cos inverse of this value. 1.5 will be the 2.25 minus 1 and 2.25 plus 1. So this will give you theta is equals to cos inverse 1.25 divided by 3.25. So how much theta are you getting for this one if you solve this one? Just check it out. What value are you are getting for this one? What value it is are you getting for this one? Which one? 90, 67, 56. Just do this calculation. Just divide by the this one. I mean the 1.25 divided by the 3.25 and take the cos inverse of this one. So it will become, what are you getting for this one? What will it become? Okay, so 67.4, yeah, the B part. So B part will be the right answer. 67.2, the 38 will be the right answer for this one. Okay, so this is the also the another way there you can find out the how to find out the angle between if you have given the direction one. So there you can find out also, and otherwise if you have the knowledge with the perpendicular directly, if you find out for the some of the cases is it is difficult just to find out the direction between them. There you have to consider it. I mean the take the this cross product or find out the value where it is I mean what the angle between them one. Okay, so okay, let's move to the next question. So next in the next question, what they are the closely pegged direction that lie on the 1 1 plane of the FCC crystal structure. Okay, so we all know the FCC structure, that is this one is my FCC one. Here again you all know about this is the FCC one. In the FCC one, which one is the closest one? This is the 1 1 plane is my the 1 1 is my basically the closely plane one. For the 1 1 plane, if I'm considering the this 1 1, let's see, this is, there are the, okay, not this way, let's take this way. What can be the possible direction? This is the one way, this is my x, y, and z. So this can be one direction, this can be one direction, this is also direction, this is also direction, this is also direction, and this is also direction. Okay, so this will become, this is at the 1 1, at the intercept of 1 1. So this direction will become, if you consider, this will become the 1 0 minus 1. This will become, how much it will become? So this will be the 1 0 minus 1, and if I'm going this way, so this will become the 1 1 0. Okay, you know how to find out this direction? I mean I think so. So because the coordinate of this one will be the 1 0 0, here it will be the 0 1 1. Okay, 1 0 0 0 1 1, or it will be the 0 0 1. Now if I have to find out the this direction, so this will be the this minus this one, so it will become the 0 0 1 minus of 1 0 0. So this direction will become this way. So this will become the minus 1 0 minus 1. Okay, minus 1 0 0 and the 1, not the minus 1. This is the 1, this is the 1. So this direction will become this one. Okay, if I'm considering this direction, so this direction will be the 0 0 minus of 0 0 1. So this become the 1 0 and the minus 1. So this direction is the 1 0 minus 1. Similarly, you can find out for the other one here also, because you know the coordinate and you can find out the direction one. Okay, so there, if you find out and you will come up with the six, I mean the different set, this for the this one, you will get the, if I'm these, if I'm considering this 1 0 0 plane, if I'm considering this plane now 1 1 0, these are the only the set of this set of family one. So for this one, corresponding direction will come out to be the corresponding plane 1, 1 0 minus 1. Another will come out as the 1 0 minus 1 as well, and from here it will come out the minus 1 1 0, and it will become, so 1 minus 1 0 here also, and it will become 0 1 minus 1 and the 0 minus 1 1. It will, if I'm considering the this set also, this one, this lead to the six plane one. So these are the six plane. One of the negative, if this is contest, one of the 1 0 is here, here 1, oh, this is the same, so this will become this one, a 1 negative here, this one and this one. So these are the six plane otherwise. So we have to find, okay, see, this is the closely pegged one, so the corresponding direction, so this 1 0 plane having this also the same plane, so this is the direction, yes. Another one is the minus 1 0, yes, this is the same as the minus 1 0. This direction also, this is also the closely pegged. And another is come out to be 0 minus 1 1. Yes, if I'm considering this only, so there is also possible the minus 1 0, and the, if I'm for this, for the negative one, so this will also giving me this 1 1, and the negative of both will, this will also give me this one. I mean, there are the many possibility of the direction. If I'm saying the, if I'm changing the origin one, so there's correspondingly your direction will also change. And the for the this plane, because this is also having, so if I'm taking the positive one, so these are the all are the equivalent one, so this will be the right one. For the one see this is the plane na? So direction will be the this one, and these direction are equivalent to this one, so this is the right answer. Another case is the one direction. No, one direction will be the body diagonal one, that is not the closely packed. We have the plane this one, so that come out to be perpendicular, coming out perpendicular from the origin this one, so this can't be possible. Another one is the only in the x direction or in the y direction in the C part. If you see the in the C part, so this is the in the x direction or in the y direction or in the z direction. No, this also can't be possible because we are talking about the this 1 1 0 plane. So this is was not solvable. Another one is the minus 1 0 1, and this is the similar to the this plane, because this plane is also lying in the 1 1 plane, this direction, because this direction has the 1 1 0 na? So this is similar to the this one. So this D and your A part are the equivalent, having the different direction sets for this one. So these are, because if I'm talking the closely packed, so 1 1, so these are the corresponding one. Okay, let me tell you for the different FCC. Okay, for the, if I'm considering the FCC one, because this is the FCC one. For the FCC one, the closely packed plane will be the your closely packed plane will be the your this 1 1 1 family, and the closely packed direction will be the, what will be the direction, because we already discussed this 1 1 0 1, so this will be the closely packed. And if, because see, it is only we have discussed only for the FCC one. If I'm considering for the BCC or the FCC, so BCC has the closely packed direction, that is in the direction of the 1 1 this direction, in the 1 1, because that is the body diagonal, we have the atom at the body diagonal, so that the body diagonal direction will be the closely pegged one. For the HCP, for the HCP we have the closely packed, that is your basically 0 0 1, that is the your plane, if I'm saying, and the direction will be the 0 1 0 same, or if I'm writing in the 4 direction, this will become the 1 0. This come out to be the closely packed one for the hexagonal one. Okay, the closely packed and the how the loosely, these are that you have to calculate the for the the atomic packing fraction for that one also. For the plain one also, if you have to calculate, so similar thing will happen for the plain one also, how much this plane is closely packed. Same thing you have to consider the atom that is contributing to this plane, and number of effect, first you have to find the number of effective number of atoms in that plane, and what is the area of that plane, and total area of the cube, total volume of the cube, or the area of the cube. There you can find out the atomic packing fraction for the any plane, or as well as the atomic plane of the lattice as well. Okay, so this is your question number 14. Now just move to the next question, that is about the question number 15. Okay, this is the similar type of the question that we have already discussed. What is the packing sequence of the atoms in the HCP atoms? We are assuming each layer A, B, C is the closely packed. So what will be the for the HCP, that you have to tell me. I have already discussed for the FCC and the uh, HCP and the FCC one. So now you have to tell me which one will the correct for the this one, for the HCP one. Which one will be the correct one? For the HCP one, which one will be the correct one? Now you have to tell me. Tell me the for the HCP. We already discussed the HCP and the FCC, the sequence of the HCP and the FCC one. So tell me the which one is the correct one. Yeah, B, it will be the B. Yes, Isaac and the Pani, you both are right. B will be the correct answer for the HCP. It will be the AB, 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 and FCC. It will be the ABC, 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 and the ABC one. Okay, okay. So this is all about the packing sequence of the atom, how the atoms are arranged in HCP and FCC one. Okay, let's move to the next question. That is the choose the correct relation between the plane and the direction indices of the four-axis system in the hexagonal crystal. So what will be the in hexagonal? We have already defined the my plane is defined as my H, K, I, L, and the direction is my represented as the U, V, T, and W. So what are the possible condition for the plane and the direction, and the direction for the this four axis system one? What I have already discussed. This is my for the this one. This my H plus K plus I should be equals to 0, and for this one also this is your U plus V plus T is equals to 0. So this is the possible, because we define I is equals to basically minus of H plus K, and T is basically minus of U plus V. Also for the this one, this is easily this is, if I'm in the 3 axis, just remember for the 3 axis what is the notation for the 3 axis system and the 4 axis. Again I'm repeating, for the 3 axis one it will be the HKL, 4 axis will be the HKIL. The difference is of I, and I is basically minus of H plus K. And if I'm considering for the direction for we represent, this is the U, capital V, and the W here we represent as the small u, V, T, and the W here. So capital U is basically to equals to your basically 2U small u plus V, and capital V is equals to 2V plus U, and W is capital W is same as the same W, and T is basically minus of U plus V. This is the relation between the your 3 axis and the 4 axis system one. Yeah, C is the right answer. Yes, Pani, you are right. C is the right answer. Okay. Okay, so let's move to the next question. The next question is all about the closely packed structure of the atom tends to have. When the atoms are the closely packed, so they are having either they are having the lower potential energy or the higher potential energy, lower bond energy or the higher bond energy. That in the, I guess in the first lecture we have discussed how this is force for the atom that is stabling here. So this is the potential graph that we discussed. for any system, if that is present here, the stable it is here. So how they are having the potential energy negative and the potential energy, will it be the the lower potential energy or the maximum higher potential energy? And what about the bond energy, will it be the lower bond energy or the higher bond energy? See, if the my system are closely packed, whatever they are stable, when closely packed, they are stable. So they try to attain at the lower energy, lower potential energy, minimum energy to stable themselves. So the potential energy always it, because they stabilize at a certain R minimum. We calculated it here also, there also in the r distance. This is my equilibrium distance, whatever that is equilibrium distance, the more my potential energy at the equilibrium distance is the minimum. So the closely packed system atom they are if they are bound at the r minimum, and that at that r and minimum the my potential energy will be the lower one. So A will be the right answer for the lower. And what about the bond energy? Because R is minimum, the distance between the two atoms is R minimum. Will the bond energy will be the higher or the lower one? Yeah, bond energy will be the higher one, because they are the tightly packed. So the higher amount of the energy need to separate them both the atoms. So the my potential energy will be the lower one, and my bond energy will be the higher one. Okay. So next question is, the hexagonal closely packed lattice is the non-primitive lattice with the motif F 0 0 0, and the non-primitive lattice with the motif as the 0 0 0, 1 by 3, 2 by 3, 1 by 2, and the primitive lattice and the motif as the 0 0 0 and primitive. This question the professor has already discussed in the classroom. So hexagonal lattice we have already discussed with the three I also draw with the three primitive lattice, that is the closely pegs, and where the motif is defined as, because this is the, if I'm considered, this will become this will, and if I say it is difficult to draw. Okay, it is similar to this one. So if I'm considering the this one, this is the, and we have the three atom here that is present here, and two here, and the one is here. So this is one. So this is the primitive lattice with this one. If I'm considering the three primitive lattice, if I'm considering one, this one, another will be with the this plane, and another third will be the three lattice with the motive at the either at the 0 0 and 1, if I'm considering at the this atom, if I'm considering this atom, or the that is half of the c distance, or that is 1 by 2, and 1 by third of this section, 1 by third of a, 1 by third of a, 2 by third of your B distance. So this hexagonal lattice, remember this, and this is always the primitive lattice with the motif at the 0 0 and 1 by 3, 2 by 3, and this is not the primitive, this is always the your primitive one. Consider with the hexagonal OD is the non-primitive, it is having the 6 no an effective number, but if this is the combination with the three primitive lattice one, and if I'm considering the one motif as here, and the if I'm considering this primitive, let's say consider at the 0 0, either at the 0 0 or at the 1 by 3, 2 by 3, and the 1 by 2. So for the hexagonal close pack one, so D will be the right answer for this one. Okay. Now move to the next question. So in the next question, what they have now, the body center cubic system cubic lattice have the closely packed direction along the 110, closely packed along the 111, and the closely planes on the 110, and the closely packed plane on the 110 and the 111. So in the for the body center we already discussed one the which one will be the closely packed direction. I mean the that is also the board. I mean the closely packed direction will be the along in the. I mean if I'm consider, yeah, origin at the center of the base one. Yes, yes. Here, if motive is considered here, yes, fine. Because we consider here this direction is the A1, this is my A2, this is my A3, and this direction that is my the C direction A3, and this is my C direction one. Okay, got it. Okay, so for the this one body center, as I already discussed, for the closely packed direction of the plane will be the around in the direction of, because the body center, that is the body center, so the closely packed direction pegged on the 1 1, and the direction is also in the along the direction of the 1 1 1, in the direction same as the D and the B. Yeah, this is in the same. Remember further this for the FCC one, as I already told for the FCC, BCC, and the HCP, which one is the closely pegged direction and the closely pegged plane as well, and find out the, I mean, so that it will be the convenient for to visualize the thing. Simple thing is that body center, because we have the atom at the body at the center body of the cube, so the whatever the direction that is passing through the center, I mean the at the body diagonal, that direction will be the closely packed, and the plane as well as that will be the closely packed. For the FCC one, the plane should, the because we have the in the FCC thing is that the atoms are presented at the at the center of the face as well. So if we consider the three face somehow, so that's why we are getting the 1 1 plane is the closely pegged, because there we touch the only three atom. There is no possibility other than getting the more atom to be in a same plane, and that can be closely pegged. So 1 1 will be the for the FCC one, and for the HCP we have the or in the one direction, or say this is in the X direction, because same thing is happening. I mean for the one plane 0 0 1 or the 1 0 0 1, that will be the direction one. Okay, so this, yes, this is all about the assignment number 3. Okay, so any doubt in any question, I mean, so that we can discuss that one. We have time. I mean, I think you joined the late, so we can discuss question number 1 and 2. I mean, of the Miller indices of the plane. Either first, I have already told you how to calculate the Miller indices for the plane. So this is for the simple cubic one. For the plane, I mean the intercept, you can calculate, and it is given here also. So you have to take the reciprocal and find out the smallest set of the integer. That will you give you the Miller indices. Okay. So this is the question. Okay, you don't you can find out this in the folder one as well, and also in the video link also there also. Check any of the question, in any question. If you have any doubt, then we will discuss that one. Miller indices of the plane. In the first question, I'm just reviewing the each question of the assignment. So just let me know when if you have any doubt in any question. Okay. So in the first question, you have to calculate the Miller indices of a plane. That is, the intercept is also given in A, B, and C the direction. So you have to find out the Miller indices. Simply take the reciprocal one and find out the smallest set of the integer one. In the second question, and there also the Miller indices of a plane, that having also given the intercept at the 3, 2, and the C along the 3 crystographic axis, and there you also have to calculate the Miller indices. So there you can also find out the Miller indices take, because A and B, C are the primitive vector of the lattice, so first divide that and find out the what are the intercept in the direction of A and what are the intercept along the B direction and the C direction one. And after that, take the reciprocal and multiply with integers so that you can get the smaller set of the integer. That will be your the Miller indices one. In the hexagonal, now how to convert if somebody has given the Miller indices for the 2 1 0 and the -1 1 3. So how you can write in the 4 axis system? There you can also uh, what will be the criteria? Just you have to remember this h plus k plus I equals to 0 for the plane one, and if I'm considering for the uh, in the direction there also your t will be the minus of u plus v also, and we also discuss the same kind of the condition in the later question one. Okay, this is also the packing fraction of, somebody asks you the packing fraction, so packing fraction is just packing fraction is basically the n effective and volume of the one atom into the volume of the lattice cell. N effective for HCP is number of effective atom in the, for the HCP will be the 6, for the BCC it will be the 2, for FCC it will be the 4 1. And simply, and you have to remember the what is the relation between the A, the lattice constant with the R radius of the atom in the all the cubic lattice system, in the all the lattice system, and there you can find out the what will be the atomic packing fraction for all that one. Okay, and if, and also you know there is no question about the coordination number. However, if I'm just discussing here also, what is the coordination number of? We also discussed in the, I guess in the last class, but I'm again repeating this, the coordination of number of the this one cubic one. How coordination is the number of the nearest atom. So number of the nearest atom in cubic one, in the cubic lattice. If somebody asks in the cubic lattice, what will be the coordination number? In this, see, remember the your coordination number will be the atom are present at the corner. Each atom will be the shared by the 1 by 8. So coordination number for this atom, how many atom are the closest one? Nearest atom one. If I'm taking this one, so this one, this, again here, back one, down one here. So how many atom will the for the cubic one? It will be the 6 one. One in this direction, backward, above, here, and downward here. So 4 direction and 2 up, 1 and down. For the cubic one, it will be the 6. For the HCP, so HCP that is your hexagonal, closely packed one, closely packed one. Your coordination number, that is the coordination number, will be the coordination number will be the 12 one. For the FCC, for FCC, the coordination number, remember this thing, I mean this will be helpful for you. I mean FCC one, the coordination number will be the 12 one, same thing, because they have the same atomic packing fraction as well, remember this one. And the, for the BCC, for the body center, because the central atom, if I'm considering the central atom, that atom is nearest to the, or the only the, in the last class we have checked this, the atom that is closest to in the body center will be the corner one. So the coordination number for the BCC one will be the 8 one, because the center atom is nearest to the all the corner atom of the that are present there. Okay, so this is all about the coordination number and the packing fraction one. There again you have to find out the Miller indices of the this shaded region one. This is also, and now again you have to find out the direct index intersection of the two plane. We, if you have given the two plane, and you have to find out the direction of the intersection of the both the plane one in a cubic lattice one. And now the perpendicular direction, that is perpendicular to direction of the which plane, there is, you can find out with the that formula that we have also discussed there. You can find out also there to consider this direction as a lattice vector and find out which one is the perpendicular to the this one. In the eighth question, you have to, we have discussed the FCC one. FCC, what is the sequence for the FCC? atomic atomic arrangement for the FCC and the HCP1. There you can find of A, B, C and the AB1. Equivalent direction for the tetragonal. Tetragonal, you know, all the sides are not equal, so your A, B will be equal, but C is not equal. So what are the equivalent direction for the tetragonal that you have to find out? And for the this question number 10 and 11 is basically about the symmetry elements. So what is the 4-4 symmetry? Second fold in the horizontal and the vertical mirror. 4-fold will be the angle will be the 90. Rotation angle will be 90. 2-fold will be the 180 degree. This is for the simple one. I guess you don't have any query for the question number 11. Question number 10. Okay, again. So, yes, let me know. What's the problem? So, what kind of the symmetry do you have in, I mean, question? Do you want to take the why it will not be the same? I mean, 90 degrees. This is the lattice plane. I mean, that is only consider we just only consider this part only. This is the infinite one, no? Just one, infinite one. This is the infinite one, infinite one. Not the this is not the just only with the 4 and the 5 ratio atomic number one. In the question number 11, I think it is clear now. I guess, Pani, what you say? Is it clear? Yes. Okay. So in the 12 we have discussed this is the plane spacing between the different planes and how we can calculate the interspacing of any given HKL or the interspacing distance that is given by A and root of h square plus k square plus L square. Sorry, this is will be the L square, and we have to find out for the 200, 100. Correspondingly, we have find out the interspacing distance, and we have took the ratio and find out the how they are related. 200 and 1001. In the next question, we have the two direction that is find out, and in the tetragonal, we have the different A by C ratio is given that is 1.5, and we have to find out the angle between them. So consider the direction as converted as a lattice vector, whatever the lattice vector, and now simple we have two vectors and find out the angle between them. So consider simple. This is the simple way. This is the very simple way you can find out the any angle between the two directions. Consider the any direction in the lattice vector and find out the with the cos product, not the cross product, the dot with the dot product or the cos theta. You can find out the angle between them to the between the direction or the between two lattice vector. This is the way. In the 14 you have we have discussed the direction in which what are the direction that is possible for the FCC1 or the 1 plane that are the closely packed one. Okay, and the next question, there's the same sequence one for the HCP. And we already discussed about this. So 16, what are the conditions for the three axis system and the four axis system? How one can convert the three axis system to the four axis and the four axis to the three axis. Remember these condition one. So it will be helpful to convert the either of one of them if one is given to the. In 17, what is the closely packed structure of atom tends to have? For what criteria they have the lower potential energy and the higher bond energy. In the question number 18, we have discussed the hexagonal peg lattice is the sum of the three primitive lattice with the motif of the 0 0 and 1 by 3 2 by 3 at the 1 by 2 1 2 atom that are we are considering at the 2 atom, and the body center having the closely packed direction at the 1 1 direction and the 1 1 plane as well as the family of the plane. So we have discussed this thing, and if you have any other doubt in the other, I mean in the any of the assignment or in this assignments, please let me know. We can discuss. Do you have any other doubt, Pani? Is it clear? Everything I mean. Okay. Okay. So I mean, if you don't have any doubts, so you can, I mean, leave. I mean, goes. Oh. Otherwise, we can discuss. If you want to tell me any other things, any topic, other we can discuss that one also. We can discuss. We have time. I mean, the 10 minute left. We have basically we have time. 10 minute left. So if you have any other query, then we can also discuss that one also. About the primitive lattice vector in the last session. Okay. Did you go through that, the primitive lattice? I mean, uh, in that one, this is only the simple. Okay, you go through that. I mean, okay. So they are, we have to, I mean, see, we have simple thing is we have non-primitive. A non-primitive have the more than one atom or yeah, also. And somehow we can convert this the known what is the theta corresponding to in that example. Set A, what is the set corresponding to a set A? Okay, I don't know. Now I have to check it. I mean, where is my set A? And the I don't have I do not remember that one. I mean, which one is the set? Set A is the basically I guess the same thing. I mean the with the that is professor also discuss in the I guess in the classroom as well. Let me check the photo if I have now. Well, discuss. The main role for the primitive consideration is you have to take such I mean such atoms so that you can get the I mean you can get the only one atom in the another one also there you have we have considered. Okay. Okay, let me see that one photo one. Just a second. I can't draw it. I mean, I have just took this photo. I think my mouse will can help this one. Okay, so here it is. The set one is A. This one because we see here we have the body diagonal as well. This atom, not the same plane. One at the center, body center. I mean, at the center of the body one, but it's not at the same one. See, this one is the center of the body center one because in this one. I mean, can you see my mouse, this cursor or mouse, something else? No, no. Let me convert it the color yellow maybe. Uh, can you see this now? This one. Can you see now? Uh, this one. Yes, this is the body center one. So this is the body center because the we have atom because of the one is because of the body center and other are the column. Now in this set we have chosen this atom as a this one. We have already considered this as to make a primitive cell one. Now this will lie at the corner of one. Anyway, if you whatever atom you have to consider that extra atom and make it to the corner one because the corner if it will become the corner one simply because either if lattice one so this I mean with the I mean this will be the something because can't you let me check if I'm drawing something now this is erasing one so this will become like this way I mean are you getting my point now this will be the your one plane Another one plane will be the because of this one. This will not remain same as the body center, because we have seen the for the FCV it will become the parallelepiped one now. Similarly, it will become not the FCC, but it will have the number of primitive lattice will be the one. If you draw this plane, this one, because this is also the body center, or and take the this one, this plane, now join them only. So this will become the primitive one. Yeah, next unit. Now you have to take out the other unit cell. Course, I mean the neighbor one also is one. Now you can't draw the primitive lesson with the same this one only. You have to consider the other one, the neighbor one, the upper one, or the lower one, whatever you want to, and then you have to make the lattice. Thing is that the whatever the lattice we have, we generally in the 2D, because see in the 2D we generally see this. I mean I don't know where can I find it. I mean, we generally took this. If this is the my latest one, simple thing, we can take this one. Now, this is the primitive one. And if I have to consider the another, this also somebody can take the this unit cell. Now we talk about this thing also, but this is also the one. And if I somebody want to take it this one, so it is non-primitive one. If I want to convert it to primitive one, so I will choose this one, so that the atom will be considered either I will take this one or I will take the this one, so that it will become primitive one. So same way, so the this my body diagonal, this atom, this one, this body again, and if I'm considering the again the same plane here, this one, now you have to consider the neighbor one as well. So this will be, it's not good, but I'm trying to show you. Now this one, if I'm considering, I have considered this as a lattice, or let's say this is the my they have considered this as a direction, I guess. This one, yeah, yes, these are the, if I'm considering this one, this one is the this one, another one is the this one, and the this one. Now I will take this same as atom here, this one, so this become one lattice, another one, and it will become somehow this will be the my, are you getting, I mean this will become my uh, somehow it will connect here, because it will adjacent, I mean it will be adjacent to this one, this will become to this way. It's not good. I mean, whatever I'm expecting, but it will be the same thing like this one. Can you say it? I mean, is it clear now? I mean, no. Uh, y- let, I can try once again. I mean, because it will be the. Uh, mm, this is- I don't know what is happening. This I'm hoping so. It will make a lattice. Okay. So one will be the this is one we consider. Another one is this one. No, no, don't. This one, and another one is the this one. Okay. Now this is not at the thing is that this is not at the same plane. These two are at the same plane, but this is not at the same plane. So again, if I'm considering this one and this one, these are the same plane, and this is at the between. I mean, let's say this way here. I mean at the highest, so that it can't. So if I'm connecting this one, so this plane, this is similar to this plane. Now this will be the body center to this one. It will be somewhere like this way, or you now the body center of this plane one also there, and it will be like this will be the lattice one. No, I have done something wrong. This is the one. Oh, just a second, just a second. Array. I have done something else. One atom is here, one atom is here, one atom is here, and the one atom is here. Okay, now this is also a one. This is one. So here it will be the for this atom we have the corresponding to here. Where am I heading? No. Okay. Okay. I this way, and let's say this is this atom. I mean, okay, and the this atom. Oh, this atom is basically at the. I mean, I'm assuming this atom to be here. I mean, this atom to be, and the same with if I'm considering no, if I'm considering this as the same one, so this will become at this one. No. Yeah, there is some mismatch. Yes. This will be the one plane. Another will be the plane from here to here, and the again with the this one. How this to this one directly when, and this will become. Now I got it. This one. Hmm. See, this will become. It will be. Now it will be like this one. See, this we have chosen this one. One lattice. This is the body diagonal. One is this in this direction, and another is in this direction. Okay. Now I have to consider this is also the body diagonal one. Just a second. Why, this is for the A2 is the y direction, no? A2, this is my this is my x direction. Yeah, this is x and this is in my y direction. This is come out perpendicularly, so this will be, and this will come out. Yeah. Okay, I will draw this in the next one. Oh, okay, for surely, because this is also I'm confusing for now. Here also, I have drawn with the rough idea with the one, and I will draw in the next class, and I will show you. Okay, how this will we can. Otherwise, I can. I mean, I can work. Okay, I will discuss in the next one. I will already will make with the this latest one and will show you. Hmm. Uh, two, the set two. Okay, okay, set two is. Okay, that will I will make one with the. Okay, I will make. I will try with the this special thing, and because I am also confusing with the this one because this is at the body diagonal and I can't see it with the if I'm taking from the top view. So this is should be come out this one. I mean, it is something like that. I mean, if we have something. Okay, this if this is something, so the board I'm talking about these two only. I mean, this is my x and y. So this angle is something. This one on I have to also take the this particular one. But it's too hard to I mean to see from the front view, and I will draw and I will show you again in the next class. We will discuss this thing point. Okay. Okay, Pani. Any other doubt? I mean, nothing. Okay. Okay. Then let's meet in the next class and we will discuss this part. Ankit, you can also, if you have any doubt, you can ask or you raise your question. Otherwise, you can leave the meeting. You can leave the meeting. Okay, thank you.